So the history of the sun weather climate studies goes back a long, long way. And over 200 years ago, Sir William Herschel, the great astronomer, noticed that the price of wheat on the London stock market went up and down on an 11-year cycle, which was synchronized with the sun. Well, he published those results, but unfortunately he coupled it with an explanation that turned out to be wrong. He thought the sun was getting sick when it had more sunspots, and so the heat coming to the earth was less, and that was why there were poor winters and poor grain harvests. So that tells us a lesson right off that you don't really want to couple your observational basis with a theory unless you've got a good solid basis in physics and chemistry and a robust model to convince the skeptics who will either discount the data or discount the theory. Now, in the case of 100 years later, you might know that Alfred Wegener proposed the theory that the continents were drifting around. And in fact, he had very, very good evidence for that in terms of matching up the coastlines, shapes of the coastlines, and the geological strata and the fossils on both sides of the Atlantic. But unfortunately, he coupled that with a theory that there were gravitational forces within the crust that were pulling the continents around, and that was very quickly shown to be untenable by a young hotshot mathematician whose name was Harold Jeffreys, who was a geophysicist, and he went on to become the president of the Royal Geological Society in England and Sir Harold Jeffreys. And so Wegener's theory about Wegener's observation about the continents moving around was discounted for 50 years. And when I was a graduate student, I talked to my geology professor, and he told me that it was a disreputable theory. Well, from those two examples, we might understand that you can have observations that will be valid, but you don't want to couple them with a theory. And unless you can couple them with a good, solid, robust theory, they're going to be discounted for a long time. Now, I hope my theories are not discounted much longer. I can't really wait 50 years to have them vindicated or disproven. I mean, I'm quite willing to agree that I could be wrong here. So anyway, from this outline, you see we need, I'm going to talk about the history. We need a physical mechanism. And one way to distinguish between mechanisms will be looking at day-to-day correlations, which I'll go into. There are 5 solar wind inputs to the Earth atmospheric electricity current system that, and also an effect of stratospheric aerosols. We have good data on how they change the current in the current system, the downward coming current flowing from the ionosphere to the surface. And we're getting good data showing how that changes clouds and cloud cover and eventually temperature of the atmosphere and the surface and winds. So I'll talk about those. But those are on the day-to-day time scale. They actually define and justify a theory of the interactions, which we can then apply to the North Atlantic oscillation, the oscillation of pressure and winds over the North Atlantic that often is a component in determining the severity of winters in Northern Europe. And I'll go into the microphysical things that go on in clouds when we have this current density in the global circuit coming down into clouds and charging up the droplets and the aerosol particles, and then we'll have some conclusions. So I wanted to point out that not only this is a graph of the number of publications per year on the subject of correlations of weather and climate with solar activity, mostly on the 11-year cycle. Some of these papers are debunking people's theories, and this is from the book by Hoyt and Shatton. The number of publications varies with the level of respectability given to the field, which, as you can see, goes up and down. And this is only up to 1992. There are over 2,000 publications up to 1992. And there's been several hundred since then, and I'll be talking about some of those. There's also been more than 20 books published on the subject of sun, weather, and climate interactions, how the sun affects weather and climate, and here's a half a dozen of them. There are quite a few more that I've been through. Well, one of the very first observational studies that's recorded, apart from Herschel, is this one where Meldrum looked at the correlations of the cyclones in the Indian Ocean from about 1845 to 1875, and it looked like a pretty good correlation of the Indian cyclones here and the group sunspot numbers. Unfortunately, this didn't continue much beyond that, and he didn't have a mechanism, so things sort of petered out. Coming up to the mid-20th century, or late 20th century, Lubitschka and Van Loon published a paper just about the time I was starting in the field, and what we see up here in the top graph, the solid line is the F10.7 centimeter flux, which tracks the sunspot number and is a measure of the ultraviolet coming from the sun, varies strongly on the 11-year cycle. This delta P is a pressure difference between these two locations. One is up there near Iceland and the other is down south in the mid-Atlantic. And so there's a definite change in the average surface pressure following the solar cycle, which is this, it's part of what's called the North Atlantic Oscillation, but only a small part. I mean, there are other sources of change that affect the North Atlantic Oscillation as well. And in the middle curve, we have the temperatures at Charleston, which go up and down by 4 or 5 degrees when you take the averages over these average yearly values and you see they're actually in anti-correlation with the F10.7, more in correlation with the cosmic ray flux. And here's one of the number of low pressure regions or storms, winter storms crossing 6 degrees west between 40 and 50 north, which is crossing basically the northeast coast of the United States. And this was in the winter months, January, February in the northern hemisphere. So I published a paper in 1988, and this is from a review I published in 1991. What we see here in this panel is the sunspot number from about 1920 up to the present. Up the top, we have the cosmic ray flux, which is anti-correlated. So there's an anti-correlation here, and there's a 22-year cycle as the main magnetic field on the sun reverses. With Jeffrey Brown and Ivor John, we looked at the latitude of storm tracks in the North Atlantic here that follow the anti-correlate with the sunspot number, and they move north and south by 3 or 4 degrees here. This is the Lubitschka and Van Loon result from a year later than my first one, and number of storms in the western North Atlantic, and down here again we've got 3 stations, Charleston, Cape Hatteras, and Nashville, all showing these temperature variations of 5 or 10 degrees Celsius. So looks like there's a real effect there, tracking the sunspot cycle for 4 or 5 cycles. And Venne Dartt, after I talked to Venne and suggested he do the analysis, he came up with this plot here. These are the winds that circle the northern hemisphere, and the length of the arrows is the strength of the wind, and the direction of the arrows is the wind direction. From solar maximum here, the winds tend to blow strongly into Western Europe in a strong zonal fashion. However, at solar minimum, they weaken, the winds weaken. These are smaller arrows as you go into Western Europe. And then there's this group in the northern part move poleward. So that's how the storm tracks shift on the 11-year cycle. Okay, and this was data from 1950 to 1980. Here we're talking about the second half of the 20th century. Now, this is a plot from Udelhoffen and Seyss that came out in 2001, and they looked at the cloud cover anomalies, the changes in percentage of cloud cover up and down by a couple of percent starting in 1900 and up to about 1990. And they looked at 54 stations over the continental United States. And again, in the second half of the 20th century, they had quite a good correlation with the sunspot number here. F10.7 is dotted, sunspot number is solid, and the sunspot number, of course, goes way back. But when you look in the first half of the 20th century, the correlation here is not good. And similarly, when they used even more stations, 90 stations, and they put a 3-year running mean in, you got good correlations here in the second half of the 20th century, but poor correlations in the first part. So now we've got a mystery. What's going on with that? And we need a mechanism to understand and to be able to make predictions about what's going to happen in the future. And unless we have a mechanism, all the skeptics are going to jump in. And Monin in 1972 said, people who talk about this produce an impression of successful experiments in autosuggestion. They're convincing themselves they've found something that's not real. Now, Joel Levine at a NASA conference said that scientists are not going to accept it, the presence of this connection in the absence of an accepted physical mechanism. Walter Roberts said the same thing. But just a month ago, a paper came out in Nature Geosciences by Chiodo et al. The paper was saying that these correlations were not real, of the North Atlantic Oscillation were not real, and they were interviewed, and the headline of the interview said that the connection had been debunked. Well, and the grounds that they used to make that statement were that they couldn't find any correlation. There was actually statistically significant correlations with their index of the North Atlantic Oscillation after 1960, but they couldn't find any before. And then they used a sophisticated climate model to show that that had all the latest bells and whistles that climate models had. And they showed that the leading candidate for a mechanism, which was the solar ultraviolet, there wasn't enough effect to account for these statistically significant correlations after 1960. And the fact that there weren't good correlations before led them to basically argue the theory was a mirage, the theory that there was a connection. So we've got a lot to cope with, and I guess you could say the same happened to Alpha Wegener way back in 1910. Well, part of the problem is that when people do correlations on the 11-year solar cycle, there's a whole lot of things that vary, both the sunspot number and the 10-centimeter radio flux, which is a measure of ultraviolet, the magnesium ion line, that is a measure of shorter wavelength, 140 to 400 nanometer solar ultraviolet, and also the total solar irradiance, which actually increases at sunspot maximum, which shows that William Herschel had it the wrong way around. The sun is actually brighter when it's got more spots than when it's not. But this effect is only about, well, a few parts in 1300. 1366, 67. Yeah, 1 or 2 parts in 1300, so around 1 part in 1,000, and that's not large enough to cause any significant change in climate on the Earth. But also we've got the flux coming from the solar wind, mainly in the Parker spiral, the east-west magnetic field, that has an 11-year cycle. It's a little bit out of phase, actually, sometimes, and it's got a different shape at times. So it's not such a clean 11-year cycle, and it has lots of day-to-day variations, as do the geomagnetic disturbances on the Earth that result from the solar wind interacting and causing these magnetic field mergers back in the tail, which propagate in and cause auroras and so on. And also there's an effect on the galactic cosmic ray flux, which goes down at solar maximum and up at solar minimum with maybe there's some slight phase delays, but they're not consistent. And the maxima are a bit broader every second cycle, which actually is determined by the way in which the main magnetic field of the sun reverses and affects the trajectories of the particles coming in from the interstellar medium. Okay, well, so I looked at a lot of data, and there's a tremendous amount of data to look at. And I decided to focus on the short-term variations because if you look back at these curves, the short-term variations are rather different between the solar ultraviolet or total irradiance and the solar wind variations. And even some of the solar wind variations, you can discriminate between things. The forward decreases of the cosmic ray flux occur differently than the magnetic activity and so on. So the short-term effects seem to be consistent with some ideas that were floating around in the 1980s about atmospheric electricity connecting the near-Earth space environment, where space weather occurs, down through the atmosphere with the surface and with clouds, although their mechanism for affecting the clouds wasn't the one that I'm going to talk about. But the global electric circuit has been known, since even before the time of Benjamin Franklin did his experiments on thunderstorms, and also in fair weather. You can fly a kite in fair weather and it'll cause electric discharge if you have a conductor coming down from the kite. And the reason is that, the theory about what was going on was worked out about 100 years ago, and the thunderstorms, they actually send current upwards to the ionosphere because the conductivity increases as you get higher up. So it's easier for the current to go up to the ionosphere than to go back down and around to the bottom of the thunderstorm. So the ionosphere gets charged up to about 250,000 volts. That's this potential V here, or I've shown it over here, 250 kilovolts. But it fluctuates as the thunderstorms come and go on a diurnal basis. There's more thunderstorms over land than over sea, and more thunderstorms in the late afternoon than the morning. So there's a diurnal variation, but also a day-to-day variation as different weather systems move in over the continents. So so we have an ionospheric potential, which is determined by thunderstorms, and then we have the current density coming down Jz, which is a few picoamperes. That's 10 to the minus 12 amperes per square meter, coming down through the semiconducting atmosphere, but it's a pretty good insulator compared to the ionosphere and the surface here. And so you can think about the resistance between the ionosphere and the surface, determining Jz by Ohm's law based on the voltage and the resistance in the circuit, and at each latitude, Rm, I call it middle atmosphere, which is the stratosphere and mesosphere, resistivity or conductivity varies, as does the RT, the tropospheric. So what's happening is we're getting this downward current Jz, which varies as all of these things, as VI varies, and there are several solar wind inputs that will vary VI, and as Rm varies and RT varies, and there are several solar wind inputs that will vary these parameters as well. So we get all these variations in the current density that have different signatures in latitude and time, and they come down and they charge up clouds. Clouds are like another resistor in the circuit, and you get a current flowing into a resistor creates an electric field across it, a voltage difference across it, which is in the same form as positive charge as the current comes into the gradient in resistivity, and negative charge as the current goes out. So now we've got electric charge in the clouds, and that electric charge then migrates very quickly to the droplets and the aerosol particles, such as condensation nuclei and ice-forming nuclei, and affects the interaction between them. Now, this is some balloon observations made by Nicole and Harrison a few years ago, and this gives you the theory about how cloud and observations about how clouds charge up. This is the conductivity here, this vertical curve here. Conductivity, as you come into the cloud, the conductivity drops by a factor of 3 in this case. We've got a cloud between about 900 meters and 1,200 meters altitude. Conductivity drops in there to maintain the current continuity. The electric field increases. And when you have a gradient in electric field by a very simple and elementary Gauss's law or Poisson's equation, you have to have the presence of excess charge of one sign. You have space charge. And so balloon observations, in fact, showed that you do get negative space charge at the base and positive space charge at the top, as expected from the smooth curve. But there's a lot of structure in it because of turbulence in the cloud. Okay, and the same thing happens actually as the current flowing from the ionosphere to the surface passes through layers of aerosols. This is some work by Rita Segalin and Foucher back in 1954. They flew an aircraft that had sensors to measure the electric field on the aircraft up through the boundary layer. The boundary layer is the region up to which the convection mixes up dust and radon and things from the surface. Lots of aerosols in it that you can see when you look out the plane on a summer's day with lots of convection. You look out window of an airplane, you can see the top of the boundary layer. Well, the electrical conductivity is going down anyway because we're getting into denser atmosphere, but it drops very sharply when you go across the top of the boundary layer here. And the positive charge nuclei concentration they were measuring increased rapidly. So most of the electric charge was now on the nuclei, which are poor conductors because they're large compared to the cluster ions that carry the charge normally, the ones that are produced by cosmic rays. So the electric field goes way up, and therefore the space charge they calculated goes way up too. And it's these layers with space charge that I'm going to focus on today, although there are other things going on electrically, even if you don't have space charge in clouds. So you'll recognize this diagram. Again, it's a north-south section through the Earth and its magnetic field and the solar wind. The main magnetic field in the Parker spiral is actually east-west, in and out of the picture here. But but it is deviated into these field lines that flow around the Earth. And we've got these cusp regions where the field lines from near the magnetic poles, they're considered open field lines. They map out and they can merge in with the solar wind in complicated fashions here and here. And then because the solar wind is moving relative to the Earth by 300 to 800 kilometers per second, what these conducting field lines down here for low energy plasma so the conducting field lines between these 2 points and the conducting Earth, to the extent that the atmosphere conducts, act like a conductor moving in a magnetic field of the sort that you have in a normal generator, where you have an armature moving in a magnetic field and that generates an electric field which drives a current. So what we have is what's called a Lorentz electric field, but it's perpendicular to both the motion and the magnetic field. So now we have a north-south electric field. Well, the positive field would be from the south to the north for a positive By if you had a pure Parker spiral and no north-south components. And that can be hundreds or so of kilovolts between these two ends of the conducting path. But it's rather diminished by the time it gets down to the Earth's surface. It does appear though, as a change in the potential, the electrical potential between the southern polar cap, which you can't see, and the northern polar cap, which is inside the aurora zone here. This is EZ, the Lorentz field. There's also a dawn-dusk electric field due to the north-south magnetic field. So we have an east-west electric field which drives these auroral currents that produce what's called the auroral electrojet, in addition to field line currents here. So there's a lot of complicated plasma physics going on there, but if you just measure the potential of the ionosphere above in the region of the south magnetic pole and the north magnetic pole, you can fly a satellite through it and look at the potential difference with respect to the low latitude regions, as has been done many thousands of times. You can use the super-Darn radar to look at the drift motions of the plasma. You find that this is a diagram from Mei Lam and her colleagues at the British Antarctic Institute that was published in 2013. The potential in Antarctica goes positive when you have a positive By by up to about 25 kilovolts. At the same time, the potential within the polar cap in the northern polar cap goes down by about 25 kilovolts. And of course, changing the ionospheric potential in this way is superimposing it on the 250,000 volts, the 250 kilovolts that we have from the thunderstorms, and that changes the current coming down to the surface, and that can be detected by electric field meters at the surface. Well, my work for the last 30 years has been on the basis that these electric field changes are important, the electric current changes are important, and they seem to be pointing to effects on clouds. So just recently we've looked at data from Alert Canada, which is within 3 degrees of the North Magnetic Pole, and measuring the downward infrared radiation from the clouds, which measures the infrared opacity, or another, it's about the same as the cloud cover. And we find that there's a dip in that. Well, there's a correlation, and if you look at the lag correlation after 3 days, the opacity has dropped significantly at 95% statistical significance now for a couple of days, and then it starts to recover. So at the same time, the instrument that was looking upwards in the infrared, measuring the cloud opacity, was accompanied by another one looking down at the surface and looking at the radiation from the surface, and that dropped in the correlation with the surface irradiance, and the By component in the solar wind dropped a day later. So the surface was cooling down as the cloud got thinner, and there was more radiation escaping to space. Well, at the South Pole, there are similar instruments looking upwards at the clouds there, and similarly we found an increase in, now it's an increase rather than a decrease because we're at the South Pole, not the North Pole, an increase of cloud opacity with the IMF-BY, which we see there. It didn't reach 95% statistical significance because here we're at 16 degrees away from the South Magnetic Pole, and so we're out on the edge of that region that is affected by the change in ionospheric potential. However, it is close to the southern electrojet in the aurora zone, southern aurora zone, which I used to make measurements looking south from New Zealand of the auroras that were there back in the 1950s and 60s. Okay, so the southern aurora zone has electrojets just like the northern aurora zone, and there's strong infrared radiative response when we have magnetic storms and we have strong electrojets, which is the correlation, lag correlation with AP here, with a lag, with very little lag actually. So actually this is consistent with some observations of clouds over Antarctica that have been made by Dominic Kniveton and colleagues some years beforehand, looking at the cloud cover from the ISCCP, which is a NASA database. No, it's a European database of cloud cover measured by orbiting satellites, and using as a reference 3 to 5 days before the maximum measured now of the vertical electric field that we are measuring at Antarctica. It's the thunderstorm-generated global ionospheric potential change. We're measuring that at Vostok in Antarctica. Then there was an increase from 3 to 5 days before to 1 day to 2 days before to 1 day before, maximized on the day of the maximum of the measured electric field and decreased afterwards. So that's a confirmation, if you like, a control on the solar wind input having that effect. We also, sometime before, back in 2008, had published data on the surface pressure in Antarctica changing as the interplanetary magnetic field By component changed. And and we did it on the basis of measurements at stations in Antarctica and in the Arctic Mamie Lamb and colleagues did it in 2013, looking at a database of global meteorological data called reanalysis data, and then we're able to look at pressure changes all the way from the South Pole here up to the North Pole, and they found that the pressures when the BY changed from negative to positive in the solar wind, and it changes as the Earth goes through these waves in the heliospheric current sheet that Joan talked about. And there's a wavy structure, and you go from the southern hemisphere, if you like, of outward magnetic field to the northern hemisphere of inward magnetic field. And those waves, you go from a positive BY to a negative BY, which is the current direction in the Parker spiral. At least once in every solar rotation, so you have a 13-day periodicity, but you also have sometimes a four-sector structure, and you have just 6 days one and 6 days the other, and sometimes it's a bit different again if there's a more complicated structure of active regions around the sun. Anyway, as you go from negative to positive, we found about 50 pascals increase in pressure out over Antarctica, over the Antarctic. There was a decrease in the mid-latitudes, southern mid-latitudes, because actually if you're decreasing the pressure here, the air has to be, or increasing the pressure, air has to be flowing from somewhere to make that pressure change, and it flows from the lower latitudes. And in the northern hemisphere, again, we had this decrease here, as you'd expect, the way the ionospheric potential goes, and a change out here in pressure. There's a much greater area at the lower latitudes than there is in the polar regions, so you don't have to have such a big pressure change to preserve the rule that the total atmospheric pressure all over the Earth is equal to the whole weight of the atmosphere. Well, the effect is strongest in the northern hemisphere winter here, and the southern hemisphere winter here. And the northern hemisphere winter effect seems to carry over into spring to some extent. Southern hemisphere winter here carries over to southern hemisphere spring here. But this is based on only 4 years of data, the December, January, February, 1998, 2001. Now we've got about 17 or 18 years of new data to work with, so we'll get much more accurate curves from that. So my theory that we published in 2018 is that this downward current JZ meeting the polar clouds, which are other special types of stratus clouds actually, the layer clouds, we've got not only the current density coming down, but we've got air descending from the upper troposphere and lower stratosphere in what's called, first of all, the Brewer-Dobson circulation in the stratosphere and the Ferrel cell in the troposphere, upper troposphere. So that's bringing down air which has a lot of very small nuclei, too small to be condensation nuclei. They're called ultrafine nuclei, 3 to 10 nanometers in diameter, and they've been measured there. And when they come down and meet this cloudy air which has come in from the oceans, which has also got very low condensation nuclei concentration, they're protected by the electric charge that's in this positive layer at the top, and there's a negative layer at the bottom, but that's carried away by the katabatic wind. And because there's the same sign charge in this charge layer, or the net charge is same sign for both the aerosol particles and the droplets, they repel each other. So instead of the aerosol particles being scavenged quite quickly with a time scale of only tens of minutes, they're repelled by the droplets, they stick around, and they can grow by vapor deposition in well-known ways from the vapors that are there in this air that's come in from the ocean. And so they can make more condensation nuclei. And if you have a higher concentration of condensation nuclei in a forming cloud, you have a larger concentration of droplets, but there's only so much water vapor, so they're all of smaller size. And the net effect on that, on the cloud opacity, is an increase in cloud opacity by what's called the Toomey effect. That's been known for 20 or 30 years. So let's see, that's these new observations we have looking upwards in the infrared are consistent, well, with some other observations. Now, I mentioned that there's several ways in which the solar wind can change the current density Jz. Now, the second solar input is because the cosmic rays change on that 11-year cycle, and in the clean stratosphere, they change more at higher latitudes, higher magnetic latitudes. This is actually a plot of the magnetic equator. So at higher magnetic latitudes, they can change up to 15-20%, change the column resistance. That's the total of Rm plus Rt that I mentioned before. The effect is mostly in the upper troposphere, lower stratosphere, because that's where the cosmic rays deposit most of their ionization. If you increase the concentration of stratospheric aerosols in that region, you decrease the conductivity or increase the column resistance, and you make that area, that layer, more sensitive to the changes in ionization produced by the changing cosmic ray flux over the solar cycle. So over the solar cycle, at high magnetic latitudes now, you can get 30 or more percentage change here in the column resistance, which translates into a change in current density. Now, the output of the current is determined by the thunderstorms, which are mainly at low latitudes and aren't affected so much by the cosmic rays, because the strong magnetic fields at lower latitude shields the atmosphere from the cosmic rays. But at high latitudes it's not. So the thunderstorms produce pretty much a constant output, but it's diverted more and more, away from high latitudes when you have a high concentration of stratospheric aerosols, and more of it flows at low latitudes. So there's a solar cycle variation which is sensitive to stratospheric aerosols, and the cosmic ray determined changes in the current that comes down at high latitudes. And with Forbush decreases, which are decreases by 10 to 20% in the cosmic ray flux, well, the big Forbush decreases decrease that amount. Todd and Niverton, way back in 2001, showed that the cloud cover decreases by tens of percent in this region within the polar cap, which is where the lowest energy cosmic rays come in, which are most modulated by the solar wind. So this is the cosmic ray connection, or one of them, and now cloud cover changes were observed by Pudovkin and Veretnenko here, and with the Russian ozone observing network, and they found that cloud cover, or at least atmospheric transparency, decreased when you had Forbush decreases, which is saying that there's an effect on atmospheric transparency, which could be high clouds, cirrus clouds, or aerosol particles, that changes as the currents change coming in during the Forbush decrease. The effect was strongest at 60 to 64 degrees, but this is geographic latitudes, weaker at higher latitudes, weaker at lower latitudes. Unfortunately, if they didn't plot the data in magnetic latitudes, otherwise I'm sure we'd have seen a stronger effect. But this collaborates the input from the cosmic ray flux that I talked about. Now, here's a third solar input, which occurs at the boundaries of these solar wind magnetic sectors, where the solar wind speed drops quite a bit as you go from the high solar wind speed region into the low solar wind speed region for a day or two. And these are balloon observations by Fischer and Mühlhausen, University of Tübingen. And back in 1962 to 1966, when the program was, the program went up to 72, but they found that the potential difference, which they integrated up using electric field meters on the balloons going up to about 12 kilometers altitude, electric field went up in the middle of the sectors and was down at the end of the sectors. They said this was for quiet sun, but actually it was a period of high stratospheric aerosol content due to the Agung volcanic eruption in 1963. And their active sun period actually corresponds to a period of low stratospheric aerosol content too. So this is telling us that the current density is affected by the sector boundaries, provided there's enough stratospheric aerosol to cause them to have an effect. Now, with my student Matt Kirkland, we looked at how the solar wind speed actually varied as we went across the boundaries between these high speed and low solar wind speed sectors, and or magnetic sectors. And the solar wind speed drops in the low speed region. Here, we're going from 20 days before the crossing of the boundary to 25 days afterwards. And the relativistic electron flux measured out at geosynchronous orbit also drops quite dramatically, actually, by several tens of %. And this measure of the storminess in the North Atlantic, well, actually, this is a global measure of storminess of winter storms, and the storminess is measured by the vorticity, the rate at which they're rotating, or rates at which they're rotating above a certain threshold of rotation within a certain area. This measures the area over the total northern hemisphere that winter storms are causing high rotation rates. And that dropped too, in synchronism with the drop in relativistic electron flux. Now, these data are all for high concentration of stratospheric aerosols from Agang and Helka from 64 to 70, from El Chicon 83 to 86, and Pinatubo 92 to 94. So, what's the connection to the North Atlantic oscillation? My student Limin Zhao is now back in China, and he's running a program looking at atmospheric changes due to solar activity. And well, here are plots of the solar wind speed without volcanic activity in the atmosphere and with volcanic stratospheric aerosols. And there's not much, and you wouldn't expect any effect on the solar wind speed. However, if you look at the index of the North Atlantic oscillation, there's no effect here in the absence of, or for low volcanic activity or for low aerosol flux in the stratosphere. But there is a dip, clear dip here for high stratospheric volcanic aerosols. So we looked at 147 events between 1963 and 2011. And again, this is in the second half of the 20th century. So that brings me to the next slide. This relates to the work done by Chiodo et al., just published in Nature Geosciences, in which they debunked the idea of a solar connection to North Atlantic weather by pointing out that there's a good correlation. This is an index of the North Atlantic oscillation going back to the 1850s or so. And this index is normalized, but it changes between sort of +1 and -1 over that period. And in the latter half of the 20th century, there's quite a good correlation with the sunspot cycle here, which is, this is their plot of the correlation coefficient. As you can see, it's better than 95% on a 40-year interval centered on around 1960. And it's reasonably high after that as well for the rest of the 20th century. But it's dramatically lower before 1960. And I think you can see where I'm going with this, because down here we've got a plot of the stratospheric aerosol optical depth measured in visible radiation. This is put out by NASA. And we've got global and northern hemisphere and southern hemisphere plots here. But this is the Agang eruption here in 1963. There's a little bit of one beforehand, and then there's Helka, another one afterwards, and then there's El Chicon, and then there's Pinatubo. All of these put up the stratospheric aerosol, and we saw changes in the vorticity area index for several years, even after the visible opacity went down, or the visible change in optical depth decreased. But actually, what the sulfuric acid that is created by the volcanic inputs does to the stratosphere is to put a lot of sulfuric acid vapor up there, which can condense on meteoric particles or even on ions and what's called ion-mediated nucleation, and that creates the aerosols. But they have to be quite big to be seen in the visible, maybe a tenth of a micron to a micron or so. Whereas there's lots of ultrafine aerosols which settle out a lot more slowly, and they last for longer and longer, I would say, 5 or 10 years. Well, so we can account for this low correlation here by, if we consider that stratospheric aerosols are needed for an effect of the changes in the cosmic ray flux. And look over here, over at 1883, we have the eruption of Krakatoa, and we have a number of other eruptions coming down up to about 1920, and we have this correlation significant at the 90% level, and the correlation is getting weaker after that. So I think this strengthens the case that a combination of stratospheric aerosols and changes in the global air current density can affect clouds not only at the highest latitudes but also in the North Atlantic latitudes and affect the weather and climate there. Clouds are extraordinarily sensitive to very small energy inputs. And actually, the very small energy input from the solar wind into the atmosphere has been a big problem for a lot of the mechanisms that have been proposed before. But clouds are very sensitive. This is a 10-mile-long racetrack pattern that was created in 1953, I think it was, by Vincent Schaefer from General Electric, flying a light aircraft, dropping pellets of dry ice from a dispenser as it flew over these clouds, which were slightly below freezing but still filled with liquid water. It's called supercooled water clouds. And then over here they did a circle around and took a photograph. And what happens is that you get a narrow region where the dry ice cools the droplets to where they will freeze spontaneously. And then they start growing because they suck up water vapor from the ambient atmosphere that is evaporating off, that will evaporate off the droplets as the humidity goes down. And so the ice crystals grow larger and larger, and they eat away into the supercooled water droplets, and you get this very large effect. So that's an instability in clouds which can be triggered by a very small energy input. That's not the one I'm going to talk about for electro-anti-scavenging, which I'll now touch on. We've done computer simulations where we have droplets falling through clouds with aerosols in them. And the textbooks will talk about a 20-minute timescale for the lifetime of these aerosols in a typical cloud composed of many droplets and many typical aerosol particles. But the Brownian diffusion gives that sort of lifetime. Well, if you have positive charge on the aerosol particles and positive charge on the droplets, or negative charge on the aerosol particles and negative charge on the droplets, you'll get this repulsion. It's really only a net effect that you have positive and negative charges on the droplets and the aerosol particles. But if the net effect is shown up in terms of that space charge that is created as the current flows through the cloud, then you get a net effect and you get a reduction in the scavenging, and that allows these small particles to stick around longer and longer and grow to be condensation nuclei size, as I mentioned, and affect the microphysics and ultimately the macrophysics of the clouds. Now, there are other things happening when you have large aerosol particles, and especially when you have large droplets, but I don't have time to go into that. And there are other things happening when you increase the density of the particles, which I don't have time to go into. This is a paper we published in 2013, but we've published another 4 or 5 papers since then detailing this. But I want to show that here we have these dots, various computer simulations of what happens to the collision rate coefficient, which you can see here is changing by orders of magnitude as we go up this vertical scale. And this is the size of the particles, so we go from a nanometer up to 10 microns. And this is the region of, this is the region here of condensation nuclei size, up to about a 10, well, they actually go up to even larger, but there are very few of them in the larger region. So if the condensation nuclei have the same sign charge, say 25 charge on the droplets and 10 on the condensation nucleus, the collection efficiency we've dropped by an order of magnitude. The net charge is rather less than that, but nevertheless you're getting quite strong effects This curve here is the curve for no charge, or the Brownian diffusion rate, except that you could deviate from that over here because of the weight effect. So we call this electro-anti-scavenging, which I think is occurring in these regions where you have the space charge. And the electro-scavenging region is somewhere else, and I don't have time to talk about that. So this is a summary, if you like, a flow chart of what's going on. On the day-to-day timescales, we see thunderstorms. This is our control. The thunderstorms change the global ionospheric potential, and we see changes in the Arctic and Antarctic clouds and the surface pressures. The solar wind drives polar ionospheric potential within the polar cap, and we see changes in clouds, and of course in JZ, as I mentioned. The cosmic rays also affect JZ and high latitude winter cloud. The relativistic electrons, likewise. The relativistic electrons only penetrate down to about 30 to the upper stratosphere. I'm sorry. So you need a lot more volcanic aerosol in the atmosphere for it to have an effect on the upper stratosphere conductivity, which is where the conductivity is higher anyway to begin with. So you need a lot of aerosol to drop that conductivity down far enough so that the relativistic electron ionization can make a difference. Okay, and solar protons, I didn't talk about those, but there's clear correlations found with JZ and atmospheric vorticity there. On the seasonal and solar cycle timescales, and even longer on multi-decadal cycles, we see these changes in tropospheric conductivity, which are accentuated with stratospheric aerosols driving storm track latitudes, zonal wind speed, and similarly with the North Atlantic Oscillation. So in conclusion now, what I'd like to say is that two categories of solar wind inputs to the global electric circuit: changes in ionospheric potential and changes in atmospheric conductivity, and they do that on the day-to-day, decadal, and longer timescales. And we've talked about these inputs. They change cloud cover, atmospheric temperature, pressure, and dynamics. And we're talking about scavenging of CCN and ice-forming nuclei, reduces the loss rates, gives you reduced loss rates for small CN, increases loss rates of large CCN, and increased contact ice nucleation. It's changes in scavenging, which can either be electro-anti-scavenging or electro-scavenging, depending on the sizes of the particles in the droplets. So we can change the macroscopic properties of the cloud, and these provide a qualitative explanation for both the day-to-day and decadal sun weather climate correlations, most of them as far as I can see. However, I want to point out and emphasize that we only have qualitative modeling so far, and we need quantitative, robust modeling based on first principles physics and chemistry to make a model all the way through from and all of these inputs to connect from the solar wind to clouds and climate. So I'll stop there. Thank you.